Yes, here we are at the physics video lecture once again. It is physics 107B video lecture 26. We're going to pick up where we left off and work through the Compton effect, an important problem, and then go back to the Lorentz transformations. We still have to talk about the Lorentz transformations in matrix form and the four-vector idea. And then we'll be ready to call it good and do a little brief discussion of what's going to be on the final exam. Okay, but for starters, we've got our Compton effect to work through. And what we're doing is we're treating the scattering of a photon off of an electron just as a collision problem. So the wavy line is the incoming photon, initial energy, and we have an electron at rest. And the electron will be scattered in one direction here. And let's go ahead and have our x-axis that way, and then the photon will be scattered in another direction. So we'll characterize this with phi and this with theta. So the energy of the scattered photon is what we're looking for. And it turns out it has a very marked dependence on the theta angle. The energy and momentum of the electron that's scattered will actually be able to remove from the problem. So this is a fully relativistic problem. Relativistic collision. And so we use the relativistic expressions. In particular, we have for the energy our Hamiltonian m squared c squared plus c squared p squared. So for the photon, which is massless, photon has m equals 0, so we have E is simply equal to c times p. So we have an energy, speed of light times the momentum. So that's for the photon. For the electron, we can use the full energy expression when it's in motion, but at rest, energy of the electron is just mc squared. So yeah, we'll make use of all those properties there. So when when the electron's in motion, this is its energy. When the electron is at rest, that's its energy. The photon always has this energy momentum relation. And yet we're also treating the momentum of the photon vectorially. Okay, so let's go ahead and set that up. This is our XY system. And yeah, I'll just write here, momentum and energy are conserved. Okay. And actually, I'll put here what we're going to use later on. So there's our relativistic collision. Then we also have the de Broglie relations. And these go beyond classical electrodynamics and even classical relativistic electrodynamics. But that's a relation of the energy and a frequency for a particle, even of mass m. P is equal to h bar k. So those are the de Broglie relations we'll actually make use of this one later on. Energy and frequency. Good. So we'll just start setting our equations up. We have momentum in the x direction. So the initial momentum, of the incoming photon, we have E over C, and since it's E0, we have E0 divided by C. After the interaction or the collision, we have E over C, that again, that's the momentum times the cosine of theta plus momentum of the electron times the cosine of phi. Okay, so that's in x direction. In y direction, of course, we just have the momentum of the electron down in our picture and the momentum of the photon up. So there we would just have PE sine of phi is equal to E over C sine of theta. Okay. There was no momentum in the y direction before the collision. So good, momentum in x, momentum in y, and energy. So now for the energy, we have the incoming energy, E sub 0, but even before the collision, we have the rest energy of the electron, which is just sitting there, that's mc squared. So E sub 0 plus mc squared. After the collision, we just have the E of the scattered photon, but we also have the kinetic energy of the scattered electron, which we're going to use there, m squared c squared plus c squared p squared square root. So we have just some algebraic operations to do. What we want to do is eliminate, this is p of the electron, right? So we want to eliminate this thing, and we can do it with these first two equations. So next, eliminate p sub electron as follows. We have, what's the best way to do this? We have p electron squared is equal to p electron squared sine squared phi plus p electron squared cosine squared phi. So the first of these two is p squared sine squared phi is just e over c squared sine squared theta. And the second of these two here, we go ahead and bring that over the other side and square it, square both sides. So that would be the plus E0 over C minus E over Z cos theta squared. Okay, so we got E over C minus E over C plus theta, quantity squared, P squared cosine squared phi. So that's just P squared. So what we'll do is, actually, this is not right. E plus, hold on. Yeah. So, okay, we're going to eliminate that. I made a little error there, caught it though. Yeah, we'll multiply this out and plug that in there. But actually, what do we have here? that was not quite right. This is energy of the photon, oh, I said it right, m squared c to the fourth, right, using that plug. Okay, I got a couple of things on the board. We got them though, c squared, p squared. Right, before we move on, m squared c to the fourth. C squared. Yeah, I said it right. When p is equal to 0, we just get mc squared. Okay, once more with feeling. So now, c squared times this p squared here. You see it's going to get rid of the c's in the denominator when I square them out. And we're just going to, so let's go ahead and do that. So c squared p electron squared is going to be equal to, getting rid of those, e squared sine squared theta plus e0 squared minus 2 e0 e cosine theta plus e squared cosine squared theta. And these two, of course, add up to just e squared. So let's see if we can go back into this expression. So now it's just a few lines that have to be done. I guess I'll erase all this stuff. Let's see. Yeah. So here's what we're going to do. Put that in there, simplify, and then square both sides. So we'll subtract off. So now we have the energy again. We'll take the E0 minus E plus MC squared. We're going to square this, and then we'll square the other thing. So we'll have the M squared c to the fourth, and whatever remains out of these things here. So e squared plus e0 squared minus 2 e0 e cos theta. So we just have to now solve for e in terms of everything else, and see what comes out. So here, first of all, we have e0 squared to e0 e plus e squared, squaring this, and then plus 2 e0 mc squared minus 2e mc squared plus m squared c to the fourth. And on the right side, m squared c to the fourth, e squared e0 squared to e0 cos theta, and a lot of things drop away now. E squared and e0 squared and e0 squared. So we now have, and the 2's we can drop, so we'll have e0 e plus e0 mc squared minus e times mc squared equals minus e0 cosine of theta. Okay, we just have to solve for e, and here, plus, minus, plus. And in fact, we'll divide by mc squared while we're at it. So mc squared squared, and the E0 over mc squared times 1, bring this over, minus cosine theta. And then we'll bring the minus E0 over to the right side is equal to E0. So good. With this here, we're ready to plug in the de Broglie relation. So I'll just remind us of what it was. So recall that we had this E equals h bar omega, h frequency, hc over lambda. Okay. So there's the hc over lambda that we're going to plug in to the E here, and the corresponding one to the E0. And in fact, here we can divide by the E0 right now, so we'll have E equals 1 over H, do it in 2 steps, so 1 over E0 plus 1 over mc squared, 1 minus cos theta, E times equals 1. So we divided the whole thing by E0. Yeah. And now we'll make that transformation to the wavelength, so we have hc over lambda times lambda naught over hc plus 1 over mc squared minus cosine theta equals 1. And now we're finally ready to just cross multiply and multiply through. So we just multiply the whole thing over, and we finally get lambda equals, it's going to be the lambda 0 here, and then the hc will cancel one of the c's there, so we'll have h over mc 1 minus cosine of theta. So that's the famous Compton scattering formula. And I'll just put this little picture up here again, and we're coming in this point here, and we are scattering an angle theta, right? That phi isn't even playing a role anymore. So E0 and E in terms of lambda. So now what you have to realize, you're coming in with a certain wavelength, say fixed wavelength, and your detector is up here. And as you swing that detector around, you get this very pronounced and characteristic wavelength dependence. So for example, theta equals 0, that's just, that's going to give you a 1 minus 1 is 0 here, and lambda is going to be lambda naught. What that really means is that there's, for theta equals 0, there's essentially no interaction. Okay, that's why it's just blowing straight through. So that's a consistency check, but for any other angle, you're getting this really pronounced relationship, and it has Planck's constant, the mass of the electron, and the speed of light. Okay, so yeah, it doesn't get any better than this. That's an amazing result. it's just a consistency check of all time for the validity of all these relations, the quantum mechanical one and the relativistic one. Okay, good. So we have that. And there are many other applications of this type. We did a couple in the homework problems where you're using the relativistic examples and getting really interesting results. Of course, this is just one of the most famous and impressive. Okay, so we have that. Now I want to come back to something that we didn't really get into, and we won't go into that deep for lack of time, but the 4-vector formalism. So we're going to go back to the Lorentz transformations. What I'll do is put them in matrix form and introduce the interval, and that'll take us right up to the point where we started doing relativistic mechanics. We'll kind of segue into stuff we've already done, and that'll give us some completion here. So we're returning to the Lorentz transformation, and the first thing we're going to do is look at it in matrix form. So Lorentz transformation, when I write here next, this is stuff we could have done before, but we're going to take it right up to the point where we started doing relativistic mechanics again. That'll take us to the relativistic momentum and energy expressions by a different route. The way we got them the other day was through an action, right? A Lagrangian approach. Good. So Lorentz transformation in matrix form. And we're going to write things a little bit differently. So I'll just, let's see. Yeah, it will do. I'll put down what we had. Gamma was 1 minus p squared over c squared. So yeah, we had x prime, y prime, z prime, and t prime. Gamma x minus vt, y, and z, because we were doing the boost just along the x-axis. And then the t prime was gamma t minus vx over c squared. So when you write them in this form, and you can also call the v over c equals beta. Don't know if I had written that before, but it's just a definition, v over c. What you see is you can imagine a 4x4 matrix in which your x, y, z, t is converted to x, y, z, t prime. Okay, because there are linear relations, right? The right side of these are all linear in x, y, z, and t. So that's what we're going to do next. Linear relations, that implies that we can put them in a matrix form. So we're going to replace the primes with overbars, and let's just set up the way we would a matrix. Vector is matrix times vector. And overbars and superscripts. So we've got x0, x1, x2, x3, and we've got x0 overbar, x1, superscript, x2, x3. Okay, so those are the primed and the unprimed. And what is this x0? Right, we want everything to be on the same footing, so we introduce x0 is equal to ct. Right? C is this universal constant, so we can express times in terms of length simply by multiplying time by c. Yeah, and so with that, these relations here, we can just read off. We've got gamma minus gamma beta for the t, right? Gamma t, gamma the beta, the b over c. Okay. Yeah, actually the beta is the b over c. Good. And then here we have minus beta gamma. Spread these out too much. Okay, gamma minus gamma beta. 0, 0. Yeah, so row times column. Good. So minus beta gamma. Gamma. 0, 0, 0, 0, 1, 0. 0, 1. Okay. So that's just a matrix multiplication. And then any other direction is going to be a matrix of this form as well. Not exactly this form, but a matrix with the property that it's just transforming one vector onto another. So once you have one, you could apply transformations to this matrix to achieve all the other possible directions. So we're going to put a shorthand for this. And yeah, so right directly under this, I can write x over bar u is the superscript, and this transformation matrix lambda u u, and so this is a row and this is a column x u. So this is the summation convention in which we leave off the sigma and sum over the index that comes up twice here, right? So the component is mu, you sum over those, and it's tagged by the mu right there. Yeah, just to make that explicit, maybe I should have done this one first. If we were summing, we would have done this. 0 to 3, 0, 1, 2, and 3. But we just leave it in this form. Okay, so now we have 4 vectors, and we want the 4 vector scalar product. And the 4 vector scalar product, I'm just going to say for 2 vectors, each one, you know, A and B are both 4 vectors. It's minus A0, B0 plus A1, B1 plus A2, B2 plus A3, B3. So the 4 vectors have the components 0, 1, 2, and 3. Now, we've got a formalism for upper and lower indices, so we're going to call covariant is if we write A mu, and contravariant if we write A with a superscript mu, and for the covariant I'll go with this explicitly A0, A1, A2, A3, But if we raise the index, we just give the first index 0, index a minus sign. So minus a 0. So that the raised index, raised or lowered, gives you a minus sign. The other ones stay the same. Right, and this of course is the one that was associated with the time. Yeah. So then that scalar product is leaving out the sum, A mu, B mu, like that, summing over mu, 0 to 3, 1 to 4 is 0 to 3. And because we're only changing the sign on this first one here, we can say that would be the same as A mu, B mu, with the lower index, where we switch those. Okay, so with this formalism, I'm going to actually hold the invariance with respect to this Lorentz transformation. We'll do in a moment. Okay, good. So with this formalism, we're going to introduce the invariant interval. Good. Invariant interval. So we're just going to name this a display. We're going to start with a displacement vector. But now we have space and time on equal footing, so this is going to be a displacement 4 vector. And that will just be delta x mu, x a mu minus x b mu. So a and b are events. They're characterized by a time and a position. Okay. So a and b are events. So time and position. So there's the displacement 4 vector. Now we're going to form the interval, which is just the scalar product of this with itself. Okay. So delta x mu, delta x mu lower index, and there's a time and a space. So we have minus delta x0 squared, and then the x1 squared, 2 squared, 3 squared, we'll just call d squared. Okay, so x1 squared plus x2 squared plus x3 squared, or their deltas, we're going to call d squared. So we have minus c squared t squared plus d squared. Okay. So that, of course, yeah, I got to make sure that I say that the t is what I'm calling delta t, ta minus tp. Yeah. Okay. So very important is that this is invariant. So I is invariant with respect to Lorentz transformations. Yes, and I still have the matrix up there with respect to Lorentz transformations, because we could write this interval here as a delta x mu, and then we would have a lambda and its inverse and a delta x mu like that. So let me check whether the upper and lower. Mu, and then mu. Okay. So there were matrix multiplication from here and from there. Okay. But, and this is the key here, this is inverse and multiplies out to a unit matrix. That's not an 11, that's a unit matrix. Okay, unit matrix like that. Good, so you have that invariance with respect to the Lorentz transformation. So this object here we can use to construct some quantities, and that's what I wanted to end with. Namely, I'll make contact with our relativistic mechanics now that we have the invariant interval. So, to get to the relativistic mechanics, and actually we've been there already, we're going to construct some 4 vectors. Now, first of all, we start with our proper time. So that we had, in fact, that's where we started with before. So the proper time, we're going to have our d tau root 1 minus d squared over c squared dt. And we're going to consider a velocity u equals dl over dt. Actually, let me consult here. T or tau. Oh, okay, good. Yeah, dl dt, we're about to transform. So this is our standard velocity. What we're going to construct is a vector eta equals dl over d tau. Okay, so we're going to get a velocity in terms of, that's why we have to keep track of the difference between these two, in terms of the proper time. And this is the spatial part of a 4 vector. Of a 4 vector. Okay. And so that's eta sub 1, 2, and 3. We're going to have eta 0 is equal to dx0 d tau c, and there's the d tau right there, so that's going to be dt over d tau. Good. Good. Bc over root 1 minus u squared over c squared. So we're using the u as the velocity right there. there's our forward velocity. And next, we're going to form the scalar product with itself. Eta sub u, eta sub u, like that. Sum from 0 to 4 is going to be minus eta sub 0 squared plus eta squared, the other 3, minus c squared over 1 minus u squared over c squared plus u squared over 1 minus u squared over c squared. Okay. So what does that simplify to? This simplifies to equals minus c squared minus u squared divided by c squared minus u squared over c squared. Cancel, cancel. So yes, equals minus c squared. So in fact, that is invariant and invariant with respect to Lorentz transformations, and it's simply a speed of light squared. So now we can build something with this here. So what we're going to build, so I'm actually going to put this finally here, because this is where we're headed with this. So let's put this over here. So yeah, we found this invariance. So finally construct P mu is equal to M eta mu. And the components now with P0 and eta 0, P1, P2, P3. So here we have MC over root U squared over C squared. And these are recognizably, I'm just going to write them as a vector. M eta. So when I put the vector over the eta, that's the 3 quantities, right? When I do it without the vector sign, this represents all 4 of them. Okay. So we have M U over root 1 minus B squared over C squared. So here's where we wanted to return to. This was our relativistic momentum, from which we then did a number of things. So here, though, it's just a, not just, but it's a construction where we had something that's invariant. So if we multiply it by something that's invariant, which is the mass, it's also going to be invariant. And the way you identify this as the momentum is you look at this is U, by the way, U. You look at the limiting case and you see you're getting your classical linear momentum back. When we had our Lagrangian in action, we actually defined the momentum as the derivative of the Lagrangian. But in either case, you get this expression back that you then recognize as, by taking its limiting case. The relativistic momentum. that we had last time. And since this is just a multiplication with an m, so you'll have an m squared times these. Okay. In fact, let's go ahead and do that. So we have that, and should have left a little more room. So piece of mu. So if we sum that up, we're just going to have an m, right? M there, so an m squared on each of these. So minus m squared c squared over root 1 minus u squared over c squared plus m squared u squared. Oh, not the root, of course, we squared the root, so we have that over 1 minus u squared over c squared. Using u instead of v. So yeah, this is, again, this invariant quantity, and we recognize this as p squared, and this here as minus the energy expression that we had before. In fact, yeah, I'll finish this up in the following way. Write this up like this. So we're going to end up with mc squared root 1 minus u squared over c squared squared minus p squared c squared equals m squared c to the 4th. So we'll get that if we multiply the whole thing through with c squared. Okay, give it another c squared. And from here we could go to our relativistic Hamiltonian. So this here was E squared equals m squared c to the 4th plus c squared p squared. And since this side was represented in terms of v and this side was represented in terms of p, then we take the square root. And you could say we're back to our Hamiltonian, which we derived by a different algebraic route, but identical content here. M squared c to the 4th, c squared p squared. Okay, so I'm going to leave it at that. That at least came full circle on these expressions that we've been using. So yeah, you get the same thing. You know, when you do the Lagrangian, you're actually inventing a Lagrangian that gives you the right answer. And in a sense, you're doing the same thing here. You're inventing some quantities that give you the correct limiting case, and then you identify that as the momentum. You identify that as the energy. Good. So the last thing I'm just going to mention is what is going to be on the exam. And I found a few good problems. And I have the date of the exam as well, so exam is Thursday, May 13th. 11 to 1. Clear that up. Same format as before. I'll probably send it out a few minutes early. And problems. We have a wave equation. We have a guided wave. We have fields and potentials. So I give you some of these and then you generate those, okay? So fields and potentials. And then relativistic dynamics of the type where P equals dl dv, etc. So where we have those relations, that's not a v, that's an l, right? dl. So of the Lagrangian Hamiltonian relations, and then fifth we have one where it's some kind of conservation law, kinematic collision type of problem. Okay, so collision, conservation law, just right. So something along the lines of our problem that we did today. Conservation laws. And we had a couple homework problems along these lines, so and the Compton effect was a good one, and then so that should cover the semester reasonably well. These won't be so bad. I'll probably pull a couple of them out of the text, and let me know if you have any questions. Good. See you guys next time.